Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Khairul My group member is Akmal Rozi, Akram Roslan and Amir Ashraf. For the group assignment, our group have choose this project that we name as Solar Tracker with Photovoltaic Inverter for High Power Agriculture. Without wasting time, let me brief about this project. So the solar tracker is for obtain the renewable energy by increasing the solar cell energy harvest, since the solar platform can move to detect the sun location. And for the photovoltaic inverter, we add and combine with the solar tracker to convert the DC output from the solar panel into a utility frequency AC current that can be fed into off-grid network and then to our local farm. So this project suggests a combination of this dual solar tracker exists with the PV inverter to generate high power energy for agricultural purpose, for example water pump. The introductory about this overall topic. Malaysia, our country, energy demand like the rest of the world also has rising every year. However, there is still some non-renewable energy like coal, natural gas and other fossils still being used in our country for generation of the electricity. However, excessive usage of this non-renewable energy can give environmental impact due to the greenhouse gas emission and some climate changes. Both of these cases have social and health implications to the society. That is why the world today need to revolve with renewable energy, which is a clean source that can give a low maintenance and production other day. So this is basically our purpose project to help the agricultural sector. So as we can see here, the upper one is the platform of the solar tracker panel, so it can rotate according to the high density sunlight. And the below one is the PV inverter, which it will convert the DC from the solar panel and then convert it to the AC, since the inverter is the function to convert from DC to AC source. What is the motivation behind this project that make us want to run this is because we find out the water shortage is significant issue in agriculture. So we need an alternative source to make the agriculture more effective. So we find out the solar pump on the market that provide power for lifetime, but the cost is significantly higher and make it difficult to be purchased for farmers. So the solar pump, we find out about 900 to 3,000 ringgit. So therefore we want to propose this combination of solar tracker with PV inverter to increase the efficiency of the energy usage to the farm.
Okay, next we move to the literature review. Now we look to the working principle of solar tracker. First idea of solar tracker is the solar panel surface should be placed directly facing the incident light from the solar radiation to optimum energy capture. In a research nowadays, a fixed solar panel system when facing a single direction receives less than ideal energy from the sun. So we must adjust the position of the PV panel directly to the sun continuously, and we can do that with implement a solar tracker. Okay, next, the angles that define the sun's location are the solar elevation angle and solar azimuth angle. And when the sun is perpendicular to the solar PV panel, so the amount of energy captured from the sun is maximized. Next, we look for the review of LDR based dual solar tracker. LDR is a sensor that is as a feedback mechanism for solar tracker, and the minimum number of sensors for effective tracking should be roughly 4 LDRs for east-west tracking and north-south tracking. So we can look here. Akmal and Chakraborty have created a dual-axis solar tracker with 4 LDR sensors, 2 servo motors, and an Arduino microcontroller-based control system. There are 4 sensors here: sensor 1, sensor 2, sensor 3, and sensor 4. All those 4 LDR sensors are mounted in the north, south, east, and west to track the sun position. Then, according to the results of the trial, the solar tracker produced 40% more energy than the previous panel. However, because to the perturbation of the environment or the bad weather of the day, LDR has a low precision, making it untrustworthy. And lastly, we look to interleaf flyback topology. Actually, flyback topology is a low cost among the isolated topologies. In the design, there are 3 cells of the flyback converter are interleaved, and there is a decrease in overall cost of the inverter system and its compact size. And the flyback converter is a low cost converter with less number of components, as the inductor for energy storage is combined with linear transformer. A total of 3 switches and combination of indicators and linear transformer is interleaved in a 3-cell flyback topology. However, the flyback converter with the transformer results in large leakage, flux, and poor energy transfer capability due to poor coupling in each transformer. Therefore, to overcome these problems, a common linear transformer for 3 cells is used, which reduces the overall leakage, flux, hysteresis, and eddy current losses produced by individual transformer and increase the coupling.
Right, we move on to the methodology. The PV source is connected to a converter based on the interleaf flyback topology via the decoupling capacitor. The capacitor supplies energy to keep the voltage stable if the input voltage drops quickly. MOSFET as the switch and inductor for each cell, and the secondary side has a linear transformer that is common to all cells and the diode for each cell. MOSFET switch is employed on the primary side because of its low switching losses and good dynamic performance. The magnetic field is where the energy is stored. Because of the present, the energy stored through the on time period doesn't reach the grid. The energy stored in the form of the magnetic inductance is transferred to the grid in the form of current during the off phase. As a result, the grid output is sinusoidal current and voltage. So this is table 1 of the PV inverter design specification. Maximum power 12 watt, open circuit, panel 10 volt 5 ampere, number of panel single, maximum converter 79.96 volt, energy harvesting efficiency more than 97%, static efficiency more than 95%, grid characteristic single phase, grid current 6 amp, power factor 0.9, switching frequency 100 kHz, and number of interleaf cells is 3. Okay, for the design, MOSFET switch have a total capacitance of 100 millihenry. Okay, the size of the ripple harmonic can be reduced by the ripple frequency is increased at the same time. As a result, this design increasing the number of cells helps to achieve the desired goals.
Okay, next let's proceed to results and discussion. So it is preferable to simulate the design before executing it in practice. So in order to simulate it, the MATLAB simulating program was used to conduct the simulation in these investigations. We can improve our power supply performance, increase reliability and sustainability, cut the time to market from design to final product by using MATLAB simulations. So from here we can see that these figures shows the DC output voltage from the solar panel. we can see that the solar panel's maximum DC output voltage is between 75 and 80 volts. So this is what we have been getting from the investigations. Next, we have the next figure, which is the converter's output voltage, which is illustrated as above. So we can see that it can be reached to 140 volts at its maximums. So next we have the grid current and RMS voltage, which is shown in this figure. The RMS voltage is 100 volts and the grid current is around 6 ampere. Lastly, we have the grid voltage and total harmonic distortion, which is shown in figure 10. So the total harmonic distortion is 0.03 in this case, as seen in the below graph. So for conclusion, this project, which is centrical with photovoltaic inverter for high power agriculture, has given a new option as an add-on for a better way to improve the efficiency of the power usage by the farm through the photovoltaic inverter. So based on the interleaved multi-cell flyback converter architecture, a central type photovoltaic inverter is designed and built for small electric power system applications such as agricultural and domestic applications. In this way, the experimental results show that the inverter operates correctly and meets the design criteria. The maximum power point tracker, MPPT, controllers energy harvesting efficiency and the inverter static efficiency are both 97% and 95% respectively. In addition, the grid voltage, the total harmonic distortion is 3.02%, which is validated in the reduction of overall losses. So that's all for our investigation. Thank you.
Thank you.